Okay, so it's time for the last talk of our conference. And I would say that this conference is unique because we have 4 cool experts from the .NET team. We already had a talk by Igor Bagatov about performance improvements in JIT. We have a talk by Steven Taub about with overview of all performance improvements in .NET 6, and we have a talk by Adam Sitnik about file I/O. And finally, Kunal, we have you with a wonderful talk about loop alignment and performance stability. So could you please say a few words about your role at Microsoft team, what I do, and how you talk complement all of the other talks?
Yeah, so as Andre was saying, there are we have talks about performance improvements, but there is a very key factor to that is the stability of the performance. Sometimes you see unstable results, and it's very hard to know whether there was improvements or regressions, as you see on this slide. So I'm going to talk about most of the like stability aspect to those performance and what we did in .NET 6. So I'll start with my presentation and
Yeah,
slides.
before you start, I want to
Hmm.
just quickly remind everyone that you can leave any comments in our Telegram chat. You could also rate the talk in our video player, and if you have any question, you could also ask them in person during discussion just right after the talk. Yeah, and now it's a perfect time to start your presentation.
Okay, thank you. So my name is Kunal. I work in Microsoft since 2009. I love the space of compilers and performance investigation. I've been doing it from like last 6 7 years. Currently, I'm part of JIT team of .NET Runtime, and previously I worked on JavaScript engine, the Chakra team that is behind the Internet Explorer. I also am a collaborator of Node.js Node. Sometimes I write my blogs on that site that you see on the slide, uh, and I my Twitter is you can tweet me with any questions about .NET. So just pause. We'll pause for a second and imagine the graph that we saw on the first slide. Like, what if this kind of graph is presented to you? What if like this graph represent like stock prices or the number of COVID cases? Can we do any conclusion from this graph whether like the COVID cases are rising or falling, if the tests are happening more or less? There is no easy way to tell like what's going on. Like sometimes it is low, sometimes it is high. So uh, we see this kind of graphs every day, and it is very hard for us to know like what is going on in the .NET, whether things are improving or regressing. And this talk, I'll describe like what we notice and what things we implemented, what features we implemented to mitigate and stabilize this kind of graphs. So in today's agenda, I will start with how we triage this kind of perf issues that we see daily in our commits, and then once we do that, I will give a deep dive on the code alignment aspect, like how the code alignment is used to stabilize this kind of performance. There is also data alignment that comes into the play when there is a performance instability, and I will briefly touch base on that. And lastly, I will talk about other tooling improvements that we did in .NET 6 to catch this kind of performance issues early before even checking it in. So let's start with the first topic of triaging the perf issues. So here's the process that we do. So we run the benchmark.net benchmarks, and there are like 1,000+ benchmarks, both covering libraries and runtime areas. So we run them daily on multiple platforms like Windows x86, x64, ARM64, and Ubuntu x64 and ARM64. uh, those are run daily, like at least 10 times a day on the batch commit. So every after every 4 or 5 commits, we trigger a run that will do this benchmarks run on all those platforms. And Then we actually aggregate the results, store that in the database, and once that is done, we do some offline analysis to know that whether there was any improvements or regression introduced from the commit range. Once that is done, then we identify the issues, we file it to this repo of .NET Perf auto filing issues by our bot. So we have a bot which will do this analysis and file those issues automatically. Then we have this V team that is formed to which triages all those issues that are filed on the Perf auto filing issues, and then we make sure that those are like we filter what are real issues and what are noise, and we try to see like what changes actually has made those impact. And once we find the real issue, once we know what are the changes that caused it, we actually then transfer it to .NET runtime. So if you have seen like any issues on .NET runtime repo that are perf related, there is this all these steps happen before that, before we actually know that there are performance issues. And in the footer you might see all the links that are related of that slide. So here's a sample of what the auto file issues by the bot is. Like on the left side, you see like there are regression issues with the label of like Windows x64 or it could be Ubuntu. On the right side, there are like improvement issues. So we go through all these issues every week and then see like what are real and what are not. So sometimes the issues to triage are like very easy. Like it is a clearly we can see that okay, this was so on the left hand side there was like a the graph was low and then it bumped up, so there is clearly a regression, and then it's just matter of checking like which commit actually was present that introduced the regression. Similarly on the right hand side there is a we see that there is a improvement in the graph, and those are like really issues because they are not noisy, they are like stable benchmarks and which improved or regressed, and we know like what might have caused it, so we just transfer it to .NET runtime. So this is just a demo of how we do it. So once the issue is there, we check all the test history of that, all the measurement history of that benchmark. We narrow it down to the change. We check the before versus after numbers and see like what commit ranges were present in that timeline. So we see okay, there were this 5 or 6 commits that went in, and then we make sure that what benchmark it is dependency injection related benchmark. So we see if there is any commit related to dependency injection. There we found one, there is a dependency injection related commit, so we know that okay, this commit has actually did the improvements. So that's how we do the analysis. But sometimes there are like difficult to triage issues, you know, like the graph that I showed earlier, like in the first slide. We don't know what is going on here, like there is no code changes on C sharp side, or there is no even assembly level difference in those benchmarks, and then it's hard to know why this is there. So we our .NET 6 aim was to either like identify or filter this kind of issues, or like fix the .NET to make sure that this kind of instability doesn't remain. So in the in .NET 6, like we started filing these issues automatically using our bot. We improved our statistical analysis to eliminate issues that has noise, so we won't see those noisy issues. We are prototyping some kind of machine learning analyzer that would actually flag the noisy issues. But again, like the core problem of instability still remains. It's just like we might not see those noisy issues. There are some plans for .NET 7, like eliminate those false positive and noisy issues in our daily triage. We want to improve our machine learning analyzer to flag the real issues. Occasionally see that there is a issue that is for Windows x64 as well as Ubuntu ARM 64, but there are like separate issues that get filed, and we want to make sure that all those issues are patched in a single issue. And our like ambitious goal is to do all this in autopilot mode, you know, like if there are a bunch of commits that get checked in, we run this performance, and it finds the real issue and it just like opens a issue in .NET runtime repo without even needing this kind of triaging. So that's the dream goal for us. So as I said, like although we would eliminate this the instable issues, but still there is some underlying problem that's happening in the .NET, like why there is this instability. So I will talk about like what we did to eliminate to some extent and that. So this feature can't be explained without any assembly code. So just a warning that you will be seeing a lot of assembly code. Uh, so before we go in the code alignment, let's do a quick computer architecture 101. What happens when you actually execute your program? So when you compile and execute the program is just like a machine code, which we called as an instruction stream. And when during the execution, that instruction stream is fed into the decoder in the size of 16 bytes or 32 bytes chunk. And those instruction stream are fetched by the decoder in the 16 byte alignment address or 32 byte alignment address. So that's where like the alignment thing comes into play. So so the decoder gets this instruction stream, and then it converts those instruction stream into the something called micro ops. And those micro ops actually are then executed. So this fetching happens in every clock cycle, so in the next clock cycle, next feed of 16 bytes stream will come. Now there is this whole like mechanism, and now if there is a loop, the processor will again go back to the starting and again feed those again fetch those instruction stream and do the decoding, convert it to micro ops and execute. Now there is something called as DSB, or decoded stream buffer. And what that does is it actually caches the micro ops. So it knows that okay, there is this micro ops, and if it is getting fetched from this particular address, I would just like cache it in a dictionary. So they don't have to fetch those instructions again and again. It will like they don't have to convert it and decode it to micro ops. They are already there in the DSB. There is also a component called LSD, called it's a loop stream detector. So when it realizes that there is a pattern of the loop that is coming into play, it just shuts off the front end, like the fetching and decoding, and it just directly feeds those micro operations to the executor, and it executes until there is a loop break. Now, the thing is, the LSD will only operate if those micro operations are present in the data stream buffer. And the data stream buffer, the micro operations are only in the data stream buffer if those instructions are aligned at 16 byte or 32 byte boundary. So so it's very important that if you want to take advantage of this DSB and LSD, the instructions has to be on the like 32 byte alignment, especially if there are like loops. So you don't like if you're doing like thousands iterations, all these things are there in the DSB and LSD, and there is no efforts taken by the front end to fetch and decode them every single time. So that's the architecture behind this alignment. So let's take an example. So here in this picture, you see for Intel or AMD architecture, which is like CISC architecture. And on the left hand side, you see those addresses where those instructions are present, and those color codes are basically instructions. So there is a in the CISC, there's a variable length encoding, so each instruction size is different. So for example, the instruction, this is like 2 bytes instruction, the red. Then there is like a 1 byte instruction in blue, and then there are like 7 bytes instruction in or in brown. So this is the instructions that are coming to the executor to fetch, decode, and execute. Now let's say there is a loop that starts at that address where you see this one. So let's say this there is instruction one of the loop, and then two, three, and four. Now you see like those the first instruction of the loop is not aligned to 16 byte or 32 byte boundary. It just starts in the middle of middle address. And so in this case, like we will have to do this fetching, decoding, execution in every iteration. There is no way that you will get any benefit, like you will see performance instability. Like sometimes if the first byte is aligned to the 32 byte boundary, you would see some improvements. If it is not aligned, you will see some regressions even though you haven't changed any code. So what if we just add some kind of no ops to the address, and then push that first instruction to fall on that 32 byte address always, all the time. if you do that, then you will always guarantee to see the performance improvement, because the first instruction always guaranteed to start at the beginning of the 32 byte boundary. So that's what this feature, the code alignment, is about. Like, it basically adds the no ops to the start of the loop, and I'll give you more detail in future slides. In risk, like in arm, there is also the same problem, except the problem is less obvious because all the instructions are fixed size, so they are like 4 byte size. So you might not see it more obviously, or the alignment or the padding needs to be added is like less, but that problem still exists in the risk architecture also. Now in .NET 5, we started doing method alignments, and what that means is we started aligning the method start at the 32 byte boundary. We did it for just for Xarcs like Windows and Ubuntu x86 and x64. But if there are like ready to run code that's for if there are like hot methods in the ready to run code, we just align it to 16 byte boundary instead of 32 byte boundary. um, and then smaller jitter methods also like start at 16 byte boundary, so they are not like 32 byte boundary. And all the other methods that doesn't have loops, they just start at 4 byte or 8 byte boundary depending on what architecture they are for. In .NET 6, we took a step forward and we tried to do align the loops as well to a 32 byte boundary. So what that means is like we try to identify the hot inner loop, the innermost loop in a method, and if we find one, then we just add no op instructions before the loop, so that the loop start gets aligned to the 32 byte boundary. So if you see in this assembly code, this IG3 block, that's a loop. Like you see at the end, there is a jump back to the starting, and just before the loop start, there is a align instruction of 15 bytes. So if you see the left hand side, there is an address, and if since we added the padding of 15 bytes, the first instruction of the loop started at 32 byte boundary. So that's what this feature is, to add this align instructions, so the loop starts at 32 byte boundary. Now, how do we make sure that we are aligning all the particular loops that might be impacted from the performance stability? Like, we try to only align the innermost loop. And why? Because it is costly to align all the loops in the method, because there is a cost associated to the alignment. Like, we are adding this extra bytes of padding, and that increases the memory. So it is expensive to align every loop. um, so we try to do this like fully automatic, so developer doesn't have to specify what loop to align or what loop they think is hot. We do that analysis, and we come up to the conclusion that there are certain loops that are hot, and we'll only align those loops. So in the on the right hand side in the example, we would align the j loop because that is the innermost loop. We won't align I the outer I loop because it also has a loop, so we won't align that, but we will align the j loop. In the below there is another I loop, but let's say it is not as hot enough because this condition is triggering more often, then we might also skip aligning this loop, although it is the innermost loop, but we will skip aligning this loop. In other compilers, actually there is an option of aligning the loops, but it is like a binary 0 or 1. You either align all the loops in that method, you align all the loops in your module, or you don't align anything. So there is no fine control, but in .NET we try to add that. So developer actually has that control, but in .NET we try to do it all automatic without developer having to worry about it. There are certain loops that I want to call out, like which doesn't need alignment or which we don't align, and those are like a method or the loops that has a call in it. Now, why we do that? Because as you remember, this alignment is all about like fetching, decoding, executing in a repeated fashion. And if you have this method call, now your control is actually going back to some other address to do the fetching, decoding, and execution. So as such, the whole purpose of the loop alignment is diminished, because you're anyway doing this fetching and decoding, and with the method call it just swaps the caller and callee code, and you have to start from another address anyway, so your micro ops will be anyway flush. It will be flush with the callee's micro ops. So alignment cannot benefit such loops, so we try to not align those loops. However, sometimes the method might get aligned, or sorry, might get inline, and in that case, like, we will continue to align those loops. So now there is a concept called clone loops in .NET. So what happens is, like, if you have this simple loop, and then there is this array access. When we actually try to JIT it, we actually convert it into two loops. One is fast loop. If you see on the right hand side, the fast loop actually has all the checks done beforehand, and there are no checks inside the loop. So it just executes very fast, assuming that the array checks bound won't be out of bound, or the length is still like inbound. And then there is a slow loop, where there are this checks for the array bound in every iteration. So we just try to align the fast loop and not the slow loop, because the slow loops are infrequent and they are like only occurs in the exception code path. So we don't want to waste our memory by aligning the slow loops as well, and so we just align the fast loops. Now, there are certain times that you write a loop and then we decide that, okay, it is not really a loop. It can be just unrolled. So, for example, in this simple example, there is this I 0 to 5. You can just like unroll the loop. So there is no need of loop. And in that case, like, since there is no loop involved, we won't be doing any alignment here. So there is something that we catch early. Now, um, now you do want to do alignment, but now how do you pick, like, so what should be the size of the loop if you want to do the alignment? So so if you remember, like, from the computer architecture slide, like, the smaller the loop is, the more benefit it will get from the alignment. And so we try to prefer that, like, if it is if the loop is small, then it will get most benefits. And as the loops size become larger and larger, alignment won't help, because anyway they will be fetching and decoding for all the 32 byte chunks at the time, and there will multiple cycles are needed to bring the loop into the DSP. So so we decided that we will only align loops that can fit in a three chunks of 32 byte, so like 96 bytes long. And if the loops are bigger than that, then we will just not do alignment. And on the footer, you will see, like, there is an environment variable to change that limit if you want to. Now there are alignment boundary choices. So at what address should you align the loop? It can be 16 byte, 32 byte, or 64 bytes. The recommended boundary for all the, like, in the manual, if you see, it's a 32 byte boundary. So we just like went with that option of aligning to the 32 byte boundary. There is a little variant in adaptive and non-adaptive, and I will talk about it in a sec. But you can actually also change that boundary with this environment variable that you see in the footer. So here's how it looks with the 32 byte alignment. So let's say you have this nested for loop, and let's say there is 29 bytes of padding needed to align the loop at 32 byte boundary. So great, you get this alignment by adding the padding of 29 bytes of no op. Is that good? Well, there are certain drawbacks for that. Like, imagine that you want to align a code to n byte boundary. You will We might end up adding, like, at most n minus 1 bytes padding. So imagine, like, in future we want to align at 64 byte boundary for a loop that is just like 10 bytes long. You will end up adding like 63 bytes of padding to align that loop to the 64th byte boundary. So more padding might be added than the actual loop size. And of course that will increase the code memory that is consumed. And then there is also, remember, there is also penalty for fetching and decoding those no ops. So for example, in this previous example, like, you see there is this nested loop. So there is a outer loop ig3 that is also that actually executes again and again, and in while that execution, there is this align instruction that falls in it. So the processor has to do the fetching and decoding of that alignment instruction also. So there is a penalty for doing that. So it is not actually very good to have always like do like a and n minus 1 padding. So we call this as a non-adaptive loop alignment, this feature. So started thinking like how we can improve that aspect to overcome those drawbacks. So we came up with an algorithm called adaptive loop alignment. And what it does, it basically adds the padding depending on the size of the loop. So the smaller the loops, it will try to add more padding, but as the loop size increases, the padding will shrink little by little. The next thing that it does for the in the adaptiveness is, if if it sees that a loop can't be aligned at the 32 byte boundary because of the loop size constraint, it will try to align the loop to the 16 byte boundary instead of just giving up. So if for 32 byte boundary, if the padding is large, then try to align it to 16 byte boundary. And if the padding is also like larger for the like 16 byte boundary, then give up basically. So this is just a table that tells like how much padding we add depending on the size of the loop. So in the 32 byte boundary case, the max padding we will add is 15 bytes if the loop is very small that can be fitted in the 32 byte chunk. If the loop has needs like two chunks, then we will reduce the padding to 7 bytes. If the loop needs 3 bytes, then we just add padding up to 3 bytes. And if it can fit in 4 bytes, 4 chunks, then it will just add padding of max like 1 byte. And if all this doesn't work, then we'll try to align it to 16 byte boundary with this parameters that you see on the right hand table. And you can change the adaptive versus non-adaptive algorithm by using this environment variable that you see at the footer. So with the 32 byte alignment, remember in my previous example, we added 29 bytes of padding, but with the adaptive alignment, we just end up aligning with the 2 bytes padding and aligning the loop at 16 byte boundary, because we thought that, okay, aligning to 32 byte boundary was very expensive because it needed to add 29 bytes of padding. Instead, like 2 bytes are much better than 29 bytes. Uh, Now, there can be loops that by default falls on the 32 byte boundary, and in that case, like we don't need to add extra padding because they are already aligned. So we skip adding those the alignment for those kind of loops. Like here, IG10 loop, it starts at 32 byte boundary, so we don't add any alignment. There can be loops that are very small and so small that they can be fitted in 32 byte chunk. Like, so whenever the decoder fetches, it will be pulled, or the entire loop will be pulled in like one fetch. And even if it is not aligned at 32 byte boundary, we know that it will be fetched in the one clock cycle, and in that case, like we'll skip adding the padding for those kind of loops. uh Next, if next, if there is a loop that already is present in the minimum blocks it needs to fit. So for example, this loop is 35 bytes long, so it already needs it we know that minimum it needs two chunks or two cycles to fetch that loop. If it already is aligned such that it is already fitted in two chunks, in that case we will just keep aligning that loop. So if you see like this 32 byte boundary, those are the boundaries of the 32 byte, and this loop is, although it is not aligned to the 32 byte boundary, but it fits in minimum two chunks, and you can't do much more than that. Like even if you align it to 32 byte boundary, it will take two cycles to fetch that loop. So there is no point in aligning this loop again, so we'll skip aligning this kind of loop. Now, there is a question of where do we want to place the padding. So if you remember, and if you see in previous slides, we always place the padding before the start of the loop. But there are some better choices that we can do. So for example, like we can put the padding in a block which is like cold enough, because in that case, like that block won't be executed that frequently, and that's why like the fetching and decoding of those alignment won't happen. So there were choices of padding placement. We just choose to put the padding just before the first instruction of the loop. uh, there can be other interesting ideas where, like, let's say you have on the right side, like if you see you want to add a padding of 14 bytes. Well, you can convert that 14 bytes padding to a jump and an align instruction. So let's say if the jump instruction takes 2 bytes, you can convert that alignment of 14 bytes into a jump and then alignment of 12 bytes. So in that case, like, you will never execute, or the processor will never fetch and decode those padding instructions, because there is a jump that we have added. The another thing that I was actually trying last night is hiding the padding behind the jump, and you'll soon see a PR for this. Basically, like if there is any unconditional jumps, we try to hide those padding behind those jumps, because we know that those fetching and decoding will never happen for those instructions. So if you see on the left side, the padding was before the loop, and then we just moved it after the unconditional jump, and we still end up getting the loop aligned. It's just that the padding placement has been moved from before the loop to after the unconditional jump. So this is work in progress that we are doing. So just to recap on the algorithm that we do this loop alignment. So first we identify what are the hot not nested loops that needs alignment. We filter out all the loops that has clone calls or clone loops. We determine the size of the loop, and understand if it will really benefit from the padding. And we check if these loops are not pre-aligned. If they are pre-aligned, then we will just skip the alignment. Next, we then calculate like how much padding is needed to be added, and then we add the padding before the loop. And sometimes, if it is possible, we try to hide it behind a jump. So these are like all the things that we do in order to align a loop. So although it like sounds like simple idea to just align a loop, there is like a lot of design choices that we have to do to accomplish that. So let me talk about the impact of this feature. So if you see that since we add this padding, we are adding extra code into the generated code. So it's definitely like there is a some kind of regression in terms of the code size. So in this graph, if you see like the left four bars are the code size. So blue is like if there is no alignment, versus orange is 32-byte non-adaptive alignment versus 16-byte non-adaptive alignment, and then the last is a 32-byte adaptive alignment. So if you see the code size is slightly, I mean it is bigger than the no alignment, but for the adaptive it is still better than the non-adaptive alignment, which is because we will try to adjust the padding based on the loop size. On the right hand side, the four bars that you see are the actual allocation that we do for the memory from the runtime. So we have this notion that we try to calculate the size of the memory that will be needed to fit the generated code. And sometimes like that might be too much, because there might be some branch shortening that happens. Like we have to uh, overestimate some of the instruction sizes, and then later while actually emitting the code we actually know that okay, this much size was not needed. There is a short jump, we can do a short jump instead of long jumps. So we overestimate some of the sizes. And even on the right hand side, if you just compare adaptive versus non-adaptive comparison, the adaptive one still takes like lesser allocation compared to non-adaptive. So that was another data point for us to believe that the adaptive alignment is really like helping us without the instead of non-adaptive. This is just like another variation of that previous slide where it's just the ratio of allocation versus code size diff comparison. And again here you see like adaptive is much better than non-adaptive alignment. Now the real numbers, like how it improves the performance and stability. So this is just like a screenshot of bubble sort benchmark that we have in .NET benchmark. So in the first drop that you see around October, that's when we started doing method alignment at 32-byte boundary. So you see there was a lot of noise, and it just like the noise just reduced after the method alignment. And also the performance increase. In the second chart, that's when we do the loop alignment, and you see like the performance stabilized, the noise was reduced just because of loop alignment. So if you see this kind of performance instability in your apps, and if there is no change whatsoever and you still see this instability, probably this alignment is playing a role in it, and you can see this clearly from this graph. This is another graph that I wanted to show, and here you see like there's a loop return benchmark. It was like highly unstable, and then after method alignment it became little bit stable, and with the loop alignment it not only became stable but it improved drastically. This is the overall comparison. Like we wanted to make sure that all the benchmark.net like wanted to see the impact of this loop alignment on all the benchmark.net benchmarks. So the graph looks like this. Like the x-axis is the number of benchmarks that we analyze and that improve, and on the y-axis is basically logarithmic scale of before versus after comparison. So higher the number, the better the performance was. So if you see for the blue line, that is for 32 byte adaptive alignment, we started seeing improvement after like 150 benchmarks or so. And for the non-adaptive, like that improvement was seen after 250 benchmarks. So clearly, like adaptive alignment helped us also in this micro benchmarks for stabilizing and improving the performance. So what's coming in .NET 7? So we just like 2 days back we added this feature of loop alignment for ARM64, so that you will see in .NET 7. There is work in progress that I mentioned in previous slide of improving the padding placement, like hiding those align instructions behind the jump. And then we are also thinking of adding this loop, making loop alignment for ready to run code. So those are some of the things that you can expect in .NET 7. Now, why I love this feature, like as it sounds very simple, but there are, if you can see, there are a lot of design choices and heuristic tuning that we had to do. There were like around 200 to 250 benchmark analysis that I had to do, watch the disassembly code and making sure that they are showing the the stabilization and the performance improvement for those benchmarks. And this is like, to my knowledge, this is one of the unique feature that no other compilers have. And we publish a detailed blog post of this, and like audience liked it. And this is like one of my favorite comment. He said that it's much better than GCC and LLVM's loop alignment. So th- that so that itself like tells like this is like quite a feature that we shipped in .NET 6. Now let's switch gears and talk about data alignment. So just like misaligned code can hamper your performance instability, similarly misaligned data access can hamper your performance instability. And if you're trying to access a data that is not aligned properly at a 16 byte or 32 byte boundary, if that data access is inside a loop, you will see like degradation. It amplifies. So the in benchmark.net, we had this micro benchmarks that allocate some data once and then access it inside the benchmark code. And source of the and that is like one of the source of instability, because we often notice that there was no change in the C sharp like library .net libraries, but still we and there was no assembly difference, but we still see this instability of regression and improvement, and we try to understand why, and then we realize that okay, it was because of data alignment. So here's the like sample benchmark code that I wanted to show. So there is this global setup that happens which allocates the an array or something, and then in the benchmark actually runs the benchmark, and it will actually access the array. Now here you see the graph of that benchmark. Like there is no changes in the sorted set, but still we see this instability, and that is tied to the data alignment. So what we try to do is like we tried a feature called memory randomization. So what would do is like it will just allocate random memory in global setup for every iteration, and we invoke that global setup after every iteration of benchmark execution. So the actual memory that you allocate in the global setup that is needed for the benchmark, there is also a pre-aligned like random amount of memory that is allocated, and that might change the alignment of the actual data that is needed in the benchmark. And the idea is to see the histogram of the distribution of the measurement and then determine whether it is data alignment sensitive or not. So, for example, in this another benchmark, there is this global setup that allocates some array and then it accesses the array in the benchmark. And if we turn on the memory randomization feature, if without sorry, so without a memory randomization, you'll see that okay, it took 502 nanoseconds to execute. But if you turn on the memory randomization, you will see like the range of the measurement varies from 108 nanosecond to 446 nanoseconds. And this clearly tells that okay, when the data was aligned you get like good results, when the data was not aligned you get bad results. So this is like another discovery that we made, and we wanted to make sure that we bake that back to the benchmark.net. So the plans for .NET 7 is to turn this feature by default to some extent. Now there is this whole measurement history that we have of each benchmark, and then turning this on might change that measurement history. We have to evaluate like how that will come into play. And then there are, like as I said, there are 1,000+ benchmark. It is hard to annotate those memory randomization for each of the benchmarks, so we have to just pick like handful of them which are data alignment sensitive, and then enable this randomization for those benchmarks. So those are some of the plans for .NET 7. Some other tooling improvements that we did to make sure that we don't introduce any perf regression and then later figure out that there was regressions. So there is a tool called Super PMI in our repo, and the JIT developers use that extensively. So what it does is it caches the all the method context. So let's say you have a DLL, it will JIT all the it will cache all the method contexts that are needed in that are present in that method. And once we have that cache, we, we can just we can just run the JIT on those cache methods without even needing core CLR. So it's a quick way to run the JIT on all those thousands of methods that we just cache. And what it does is it validates the impact of our JIT changes on those thousands of .NET methods in short amount of time. Like there is no execution, nothing. We just like JIT all the methods and then see how much what was the impact of those changes. So, and it has a it has a very good feature of showing the assembly difference of the impacted method. So you give it the you run the JIT on the before your changes, and you run after your changes, and then it will show you all the assembly differences in all the methods that were impacted by your change. So this is really our gateway to merge any JIT changes. So if you're sending a PR on .NET runtime to make any JIT changes, probably you will be asked to show the Super PMI result before even like merging that PR. So so just to give an idea, like we cache like libraries. So libraries means .NET libraries methods, like all the .NET libraries methods. So there are like like almost 230,000 methods. There are like micro benchmarks method that we cache. So there are like 26,000 benchmarks, and we cache all the test methods and libraries test and things like that. So whenever we do this Super PMI as a like assembly difference, we run the JIT through all these methods and see what all methods got impacted by our change. And it has various metrics like code size difference, perf score difference, allocation size difference, instruction count difference. So it can point us like what metrics change on which method. So here's the screenshot of assembly difference for perf score, for example. Like let's say I make a change and I want to know how many methods it impacted and what were the impact. It will show you, okay, this method got impacted. There was like this much change in the method after my JIT change. So it gives us like really good idea, and it helps us understand that the perf implication from our JIT changes before even merging those changes. So this is a like really good tool that if you're contributing to JIT, you should try. So the ask from you, what you can do, definitely like try .NET 6. We love feedback. Give us some feedback. Tell us like how the performance is. And our partners were really impressed with the performance improvement they got from .NET, from switching from .NET 5 to .NET 6. So definitely try .NET 6. Contribute to .NET runtime. We love to see contributors. Recently there have been like a lot of contributions that we are getting in the JIT area or in general in the .NET runtime. So please do contribute to .NET runtime. Recently we started a process called community triages. So even if you're not a Microsoft employee and you are actually actively contributing to .NET runtime, we will give you permissions to triage issues. You will give you permissions to mark a label to the issues or merge PRs and things like that. So there's an initiative that we have started to attract more contributors. And finally, you can definitely work for Microsoft. We are hiring. There is a link that I have posted. So if you're interested in doing this kind of work, please send your resumes to that link. Thank you. That was it. So yeah, any questions, comments, feedback?
Yeah, Kunal, thank you very much for the amazing talk. It was very insightful and very interesting. And yeah, I have one question from me. So this
Mhm,
topic means a lot for me
mhm,
because I guess the first major challenge in development of benchmark.net was
mhm,
related to a loop alignment. It was more
mhm,
than 5 years ago, I guess.
mhm,
So it was early days of benchmark.net, and we
mhm,
had a serious problems with nano benchmarks. So
mhm,
the first versions of this library were pretty simple. So uh, a user provide a method. We uh,
mhm,
wrap this method with a loop
mhm,
to mitigate the stopwatch resolution,
mhm,
because it's
mhm.
not enough to measure 2 nanosecond method.
Right,
And
right.
we just run it in a loop and then divide the total time by the number of iteration. And
Mhm,
we had a problem of instability because, of
mhm,
course, from run to run we have different loop alignment, and the
mhm.
performance were changed significantly.
Right.
Yeah, and back in these days, I wasn't aware about such a serious impact of loop
Mhm.
alignment on performance. But
Right.
the thing was I did was pretty simple. It was manual loop unrolling. So we
Yeah.
live with this heuristic now as well. So the idea is simple. We should duplicate the loop body several times
Mhm,
to
mhm.
avoid having too short cycle. And
Right.
such a way we remove such a serious impact of loop alignment. So it's still
Mhm.
here, but it's not so noticeable anymore, since we have a huge loop.
Right.
And the default enroll factor in benchmark.net is 16.
Okay.
I picked it one day and it's still here. But
So
it
what is 16 tells?
hmm? we
Like
d-
what does a 16 mean?
but when you provide a method that you want to benchmark, we duplicate
Mhm.
the method call 16 times
Oh,
inside the
16
loop.
times. I
Yeah.
see. Okay.
Yeah,
Okay.
so the method is not. Basically it's bigger than 32 bytes and 64
Mhm.
bytes as well. So
Mhm.
it takes a reason. Yeah, I guess only the 32 bytes condition is satisfied. So
Right.
anyway,
Right.
it's big enough
Mhm.
to handle this issue. But this was
Right.
a heuristic that I just found manually based on several
Yeah.
empirical experiments. And I was wondering about the same heuristic in .NET. So you said a few words that you also applied loop unrolling,
Mhm.
and I know that this heuristic was implemented in legacy JIT in
Mhm.
first version of .NET Framework, but it
Right.
was missed in first version of RUJIT. So when
Mhm.
RUJIT was introduced, it
Right.
had only a limited set of heuristic, and there were no any loop unrolling. So could
Right.
you tell more about the current state of this heuristic? So what kind of loops you unroll, what kind of factors you have, why do you could
Right.
you provide any more context? I'm interested in information on that.
Sure. So yeah, I mean, as you said, like there is still the state of matter is the loop unrolling is happens in very rare scenarios. Like we are like pretty like hard coded. Like if it is like just the bounds we know in advance, and if the array, if there are arrays, if there are no exception handlings, so things like that, like there is very limitation on what we do in loop unrolling. And we have started looking into this overall loop optimization work in .NET 5. We did some improvements, sorry, in .NET 6, and we also have plans to do in .NET 7, like improving the loop cloning, improving the loop unrolling and things like that. But but yeah, like as you said, like things are still that way. Like the loop unrolling is very minimal right now, and there are like very known problems that we are aware of. I can probably like send a link of all the work items that we are planning to improve this overall loop optimizations. um, Talking about the loop unrolling that you do in benchmark.net, even though like you would do this loop unrolling and there is this loop in the benchmark.net, you don't have any control to change the loop that is actually inside the .NET libraries method. So for example, you have this benchmark of parsing, right? Like you would do like this parsing, you will unroll it to 16 times or whatever, but there is actually a loop inside the parsing function of .NET libraries, and this loop alignment actually even tries to align those loops, so you don't get this unstable result. So although like you are mitigating the stability problems from benchmark.net side, there is still those issues in the .NET libraries itself.
Yeah,
So
yeah,
so
exactly.
we try to analyze those. Yeah.
So far, we do only some basic heuristics for smaller loops, right?
Yes, right. Yeah, there are like a lot of improvements needed for loop side, and yeah, we are working on that in .NET 7.
Okay, so it sounds promising. I hope
Mm-hmm.
to see you on one of the next conferences telling us what's going on with loop unrolling.
Yes,
Um,
yes, definitely.
okay, so thanks again for a wonderful talk, and I guess
Mm.
it's time to switch to discussion. So
Okay,
thanks from the people in the audience for watching, and if you have any questions, please join the discussion as well.
thank you everyone.